My job is to introduce our speaker for this evening. I'd like to thank you for coming. I heard Mike told me that Kenny G is playing over at the Deadwood Mountain Grand, so I'm glad to see we have some people that realize that high quality science communication is better than Kenny G. So thanks for coming out. So over the last 11 years, as we've developed SURF, as you can imagine, it takes a lot of input from a lot of different people. And for us to be able to move forward and really become a world-class facility that we are today. And so from the start, our speaker tonight, Dr. Mike Wetherill, has been really a tremendous friend and partner to the South Dakota Science and Technology Authority and SURF. We're very grateful for Mike's help along the way and his counsel and many others like Mike who have been in this industry for a long time who have given us really some tremendous guidance along the way. He's been a great partner in many roles as a reviewer and counselor, coming in and giving us some tough love on how to move the program forward. As a researcher, as part of our leading dark matter experiment, the LZ experiment, which is actually installing right now and getting ready to go operational later in 2020. And also as a lab director and someone who in his role has been more than willing to lend the resources of his lab to have people come out and meet with us and help us advance our program. And so, Mike, for that, we're greatly appreciative of all the work that you've given us over the years, and Mike has played a huge role in SURF becoming what it is today. So tonight, it's my honor to introduce Dr. Mike Wetherill for our Nobel Day speaker. A bit of background on Mike. Mike currently serves as the lab director of the Lawrence Berkeley National Lab in Berkeley, California. And as I mentioned recently, was a key member of the LZ experiment. He had to back away from that as he took on his latest role. Dr. Witherell has had a highly distinguished career, including serving as the director of Fermilab, starting back in, I believe, in 1999. And Mike was at Fermi for a number of years, very successful there. Also as the vice chancellor for research at the University of California, Santa Barbara, where he also held the presidential chair in physics. And to keep it short, I'll just let you know Mike has received a lot of different awards and accolades for his work, both as a manager in the science field and also for his technical work. So in 2016, Mike was appointed as the 8th director for the Lawrence Berkeley National Lab, which was originally founded by Ernest O, a Nobel Prize winning researcher and also a native of Canton, South Dakota, if you didn't know that by chance. And throughout his career, Mike has seen firsthand the echoes of Lawrence's contributions to the field of physics. So tonight, Mike will help us discover the connections between Lawrence's innovative science back then, when he won his Nobel Prize back in 1939, and the ongoing research today, both globally here at SURF. So please help me in giving a warm welcome to Dr. Mike Wetherill.
And what I clearly need to do is get me actually I need to have an avatar too. So I realize that I've been missing that, and so I'm going to have to get my strategic communications people working on that. So first of all, let me say it's great to be back in LEAD. Set that up. I have been here many times before, but it's been both as helping to, at one point, reviewing the operations here and making sure that it was ready to go to the big time, and then I'm working on the LEX experiment, taking shifts down below. I've said this is the first time I think I've been LEAD wearing a tie. That's the difference. That's not. And let me also say, say a moment to Science Steve, how important these people are who take on these jobs in science education for the country. Everywhere, there are people in every community who are doing things like this, and how important they are for society. And that we develop the next generation of STEM leaders for our country. And I feel very strongly about that, so I'm proud to be on the same podium. So, okay, so let's talk about E. Lawrence a little bit. So this is actually the view from Lawrence Berkeley National Laboratory. I say it's the best, we call it the best view from a lab. That's in Berkeley, California. And it is just one of the many institutions that E.O. Lawrence built. And that's what I'm going to talk about today. But he started here in Canton, South Dakota, as you heard. He was born in August 8, 1901. His father was a leader in public education in South Dakota. He was the superintendent of that school, and then the state superintendent of education, president of Southern Normal College, and the president of Northern Normal Industrial School in Aberdeen. So he, and clearly, how should I say, his passion for education, as you'll see, was installed in both in Ernest Orlando, in E.O. Lawrence, and also in John Lawrence, who was born 3 years later. So Lawrence received his bachelor's in chemistry in 1922 from the University of South Dakota. That's about the normal age, 21 years. But then he started moving fast after that. He moved from chemistry to physics, and since I'm a physicist, I think that's good. He got his bachelor's in chemistry, as I said, in 22. He went to get his master's in physics at the University of Minnesota and did that in 1923. Then his advisor there moved to Yale, and he moved with him and got his PhD in experimental physics, 3 years after a bachelor's. That's moving fast, And then he continued on a fast academic track. They kept him on basically directly into an assistant professor job at Yale, where he was 3 years. And then they hired him as an associate professor, and which is also a short time for that. Hired him at Berkeley as an associate professor, and it was only 3 years before he was promoted to professor. So he was the youngest full professor in the history of Berkeley at the age of 30. So from 21 to 30, he was really moving. And he was impressing everybody as he went. But he was still just getting started, because this was right in the time that his big idea, he was getting his really big idea, basically. So I'm going to step aside from Lawrence for the moment to give you some idea of what the world of physics looked like at that time. This is probably a group of people at the most famous conference probably in the history of physics. It was 1927, the Solvay Conference. Those are the 29 people collected there. 17 of them won Nobel Prizes. And at that time, there were only 30 people in the world who had won Nobel Prizes. So most of them were there at this conference. And it's Einstein and Dirac and Bohr and Heisenberg and Schrödinger. It's basically everybody in the world of physics in some sense at that time. But it's also true, a couple of things though. There is only one woman. So, of course, Madame Curie was the unique, and you can think about what it was like, how strong she was to be able to thrive in that environment. We know how hard it can be today for women in science, but think about how much harder it was at that time. But there's also let's see, this is Arthur Holly Compton. I think he's the only American scientist in this one. And now I know it was in Solvay's in Belgium, and it was not that, but it also reflected the fact that breakthroughs in science were done in Europe at that time. That was just about to change in a big way. So at this moment in time, the recent discoveries were there'd been relativity and quantum mechanics and the atomic structure of the electrons around the atom, and that they're in shells, and what a proton was. Those were the things that they knew. What they didn't yet know is what came to be the uncertainty principle, what antimatter was. Even they knew about the proton, they didn't know about the neutron. They knew that the electrons were around this small positive thing in the middle they called the nucleus, but they had no idea what was in it or what held it together. And so people needed a way of studying that. And the other thing is these people all did their work either as theoretical physicists or as lone experimenters in their laboratory with their smaller group, because that's the way physics was done. All of that was about to change. So this is the environment that where Lawrence got his big idea. The big idea was, well, first of all, what was the scientific need? that nucleus, what was holding it together, what was in it. Yeah, you couldn't study anything that, they didn't even know how big it was. And they couldn't study that because the wavelengths of all the probes they had were too large to see any inside that. You needed something, in fact, because of the uncertainty principle, you needed something that was higher energy to even get in and see what was going on. So you need to have, and you needed to, and you have, the nucleus was this positive charge, a proton coming in would be deflected by it if it didn't have enough energy to penetrate that. So you needed protons that were millions of electron volts in energy. And no one had really done that well. And Lawrence realized that it would be easier to build a circular accelerator that could do this and to get to protons to energies greater than 1 million electron volts. And the basic idea is you have these two Ds, these semicircular vacuum chambers, and they're all, you have on this one you have a positive charge, this one you have a negative charge. When the proton goes, it gets accelerated. Okay, and they're all sitting in a magnetic field, so when they're in there, they're always going in a circle. So they spin around. By the time it gets over here, you've swapped it. So this one's positive, this one's negative, it gets accelerated again, goes faster and faster. And it just works out that takes a constant frequency to do this and a constant magnetic field. So it's actually not that hard to do. And he realized this, and this is his 1934 patent of the cyclotron. He'd already built some by then, but he said, maybe I ought to patent this, maybe it'll be useful. So that was his big idea. Now, what does it actually look like? Well, this is in there, we have, I think this one's actually at the Lawrence Hall of Science in Berkeley, but this is the 27-inch cyclotron, so, that's like that. There are the two Ds, they get accelerated there in the middle. These are all the, this is all the high-tech vacuum work you can see there. It's a little better than sealing wax. The first one, literally, the first model they did was sealing wax, actually. I mean, just to show that they could. And this is sitting in the big magnet. To get the magnetic field, you needed that much iron at that time. And he got protons with energy of 4.5 MeV, which a million electron volts. At that energy, protons traveled at 1/10 the speed of light. It turns out when it starts getting that 1/10 the speed of light, this trick gets a little more complicated. The time doesn't quite stay the same as it approaches the speed of light. And so you've got to do some extra fancier things to get beyond that. So that's part of the history of accelerators. But I would argue this marked the birth of particle physics. This is the first time and nuclear and particle physics together, subatomic physics, anything smaller than the atom as a whole, this was that birth. So I think I can make this work. This is a video, and it's one video I know of where you can actually hear Lawrence talking about this. I'd like to see if I can play it.
Now here we have a mechanical model of the cyclotron which perhaps might be helpful in understanding how it works. There are two semicircular electrodes in the vacuum chamber of the cyclotron which, so to speak, move up and down in potential. Here we have two plates that move up and down in potential, and the particles are generated here at the center, so if they start here, and this is up, and this half is down, they will go across downhill and pick up energy. And we'll start it off. Here it's up, here it's down, 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 down. The two are going up and down, so the particle always crosses the region between downhill, and therefore the particles spiral out on every winding circle.
So I thought that was nice because it's the one thing where you can actually see Lawrence for himself. The other thing is that even then, doing science education was important even then. And that is a nice mechanical model showing it. It has important points. But that thing where at the end they put up the target card, so the production values still needed some work, right? The history of accelerators is to a great extent a history of an enormous amount, a lot of science and not just physics. This is equivalent energy of basically what it would take of an accelerator, a simple accelerator to get to a certain energy from 1 million electron volts to 1 billion electron volts to 1 trillion electron volts and beyond. So that's 10, 12 orders of magnitude. And these are the years 1930, 40, 50. So you can see that the accelerators have been advanced at a level to keep it on that exponential rise up until the Tevatron over that time. And it started out with cyclotrons, and then there were synchrotrons. Synchrotrons are, you can't do it all in one magnet pretty quickly. So you have a series of magnets, but it's the same idea, and you can synchronize them. So they had the synchrotrons, and they had actually, then you started, you got past the point where you could do it with a proton hitting a target. You started having protons hitting each other, which is the way the Tevatron worked in the Large Hadron Collider. You see, we no longer, it got too expensive just to keep going on that path. The Large Hadron Collider is the biggest machine now. But the other thing is, I'm going to talk about this, many other uses for these accelerators came out, and what cyclotrons do, what X-ray machines do. So I'll talk about how many different things came out of that. And this was actually in the Tevatron. These synchrotrons are, you can see it's magnet, 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 and doing the same thing, and then they get their kick and energy, but you can't build a magnet as big as these machines. And that allowed you to make this into these massive machines that drove an explosion in discoveries about the nature of matter, space, and time, and about 35 Nobel Prizes probably coming out of this. So one path has been to the highest energies to see what has gotten through the fact we didn't even know what force held the nucleus together, to not only understanding that force, but not only what was in the nucleus, protons and neutrons, but then getting inside that and saying what was inside the proton, quarks and gluons. All that work has been done. And finally, of course, the greatest version of this is the Large Hadron Collider. Those are the magnets for there, and these massive detectors, the CMS and Atlas experiment, that do those experiments in Geneva, and discovered most recently the Higgs boson, which was in some sense the crowning jewel of the present level of understanding. So that's the Large Hadron Collider. That's that 17-mile around collider there. I was lucky to be head of Fermilab when we were the Tevatron was the highest energy machine in the world. That was about 3.8 miles around. I knew it exactly because I used to run around it for my exercise. So I did 4 rings one day. That's my record. And they're even thinking about having a 100-kilometer or a 60-mile circumference ring there. But this is something that will take some decades to develop. Both in there'll be stronger magnets than we have today. So that's one branch of what came out of Lawrence. But that's not all. It turns out cyclotrons still operate today. Thousands of cyclotrons operate today, but they're mostly for medical research. And in various ways, and I'll talk about this a little bit, cyclotrons today give low energy protons at really intense, at high intensities, which they use to, for example, make certain radioisotopes. And the radioisotope in particular, as an example, is fluoride-18 is used for PET scanning. And the way this goes is a patient, they're trying to look what's going on inside him in a non-invasive way. You inject a chemical that has fluorine-18 attached to it. The positrons, which are the antiproton electrons in there, they're emitted, they annihilate with an electron, and 2 gamma rays come out that are exactly opposite each other. And you have these detectors that see them, and you can work in and see where did that come from. And if you have a ring of these, and you do this, see many of these, you can work back and get an image of what's inside. And that's been a breakthrough. So now, but the trick is that these things have a half-life of only 109 minutes, so you can't do it at some foreign site and bring it in. that's a good thing because you want all the radioactivity to die, for it to be safe. You want it to die away quickly. You want to give it and then have it cleansed from the body. So these clinics and hospitals have a cyclotron. It's small enough in size they can do it. In a room there, they can make the stuff and then rush them out and do the work. So that's one example. They're still, of course, developing new ways of doing this. We have some Berkeley Lab scientists working with UC Davis researchers on not just one ring of these, but a whole cylinder of them. So you can basically do all the imaging at one time. It's about 50 times faster. And so this makes it, this is still experimentally developed, so you can do it with an extremely low dose. You can also do it with, for example, young patients who are too fidgety to stay in place. This actually makes it work much better, which of course is a problem. I think at Davis, they're also probably doing it with dogs because they're a big veterinary school. So they actually have a program, use them for right now. But let's talk about another completely different use, although it's using the same sort of imaging. But I'm going to talk a bit about this. But another biggest use of accelerators today are these synchrotron light sources. They have electrons in rings, and they use the X-rays coming out of them, make these exquisite, intense, focused X-ray beams that they can use to study the structure of molecules. Every drug that has been approved in the country over the last 10 or 20 years had its structure solved at one of these synchrotron light sources around the world, around the country, and mostly at places like Berkeley and Argonne National Laboratory, Brookhaven National Laboratory. This is work that used to be done with X-ray tubes in laboratories. This has taken this over. So drug companies have basically are doing all their structure work there. So in this particular case, there was they actually designed a small molecule that had exactly the right shape to fit in and block something that was needed for metastatic melanoma to reproduce. They could go in and design one, and they basically could generate a molecule, see what the structure was, do some tuning, see what the structure is, do that so fast that they before doing trials, they had this thing that they pretty sure was going to work. And when they did a test on it, this was a couple of years ago, this was sort of front page news, they were doing a test where they gave it to some people, not other people. It was so clearly successful. They had people who, these are metastatic melanoma growths, tumors. And after some period of time, the person had cleared up quickly that much. And they actually got full remission in a couple of patients out of this. That for ethical reasons, they stopped the trial so they could give that new drug to everybody because they couldn't justify, it was so clearly advanced. And that has speeded up that process enormously. So that's something else that these circular accelerators are doing these days. So that was one. So that's one line of what Lawrence created. You know what cyclotrons did, but more generally, how accelerators have revolutionized science and medicine and technology. But the other thing Lawrence did was develop, well, I would argue, a great laboratory. But more than that, the idea of team science was first done by Lawrence, what you can do with big teams. So this is the laboratory that I work at today. This is probably about 1945. This is the University of California, Berkeley. I don't need to explain that was the football stadium that was just rebuilt a couple of years ago. It's still in the same place. But down here, his accelerators were getting as big as this grand dome building here for the 184-inch. And basically the chancellor was saying, you're taking too much space, go up there and find some space up there and put your lab up there. So that's what they did. So that was it then. And that's where our national laboratory is today. This is actually, I use this photo more than anything. So to explain what we mean by team science. So here's Lawrence. He was 38 years old at that time. That was the year he won his Nobel Prize. This was his group. This was the sort of administrative staff and management. These are the scientists. So there are a few stories for me to tell out of this. So this is John Lawrence. That's the brother I told you about. also from Canton. He was a medical, he had an MD. He came and started with the very first accelerators, starting doing medical research with the isotopes that were produced there. So that was built in from the very beginning by another Canton native. This is J. Robert Oppenheimer with the pipe head sticking up. He was a 38-year-old theoretical physicist at that time. That's just before he came to start working on developing fission and the bomb and managing the Manhattan Project and establishing Los Alamos National Laboratory. This is Bob Wilson. He was a 25-year-old graduate student of Lawrence's. He came to build Fermilab. He was the founding director of Fermilab and built the biggest accelerators there. So I was the fourth director at Wilson's lab, and I'm the eighth director at Lawrence's lab. So I have a special affiliation with this photo. So this was Louie Alvarez. He was a 32-year-old experimental physicist at that time. During the war and just after, he developed ground-based radar control for aviation and won a National Medal of Technology for that. He built bubble chambers that actually saw it at where our knowledge of particle physics grew enormously. All these bubble chamber pictures, have you ever seen them, came from his bubble chambers. He won the Nobel Prize for that. And then he and his son developed the Alvarez hypothesis about how the dinosaurs died, which is now widely accepted. So he had a rather broad scientific reach. And there was Edwin McMillan, who also won a Nobel Prize. So all these people were working together at one place. And before that, it had been individuals working in their own labs. And Lawrence realized that if we get groups like this together and work together, we can do things people can't imagine. That was the beginning of team science. It's, he founded one national laboratory, he founded another one, he founded one that developed into two, Lawrence Berkeley National Lab and Lawrence Livermore National Laboratory. This was the birth of the national laboratory system. I mean, it didn't actually become national laboratories until 44, but this is how it started. But it was also the beginning of team science. Now, I tell people, so we're trying to reproduce this today. There are a couple parts here I'm not trying to reproduce today. If I had all those people up there without protective equipment today, I would be fired. And I said, I don't need to. And if I had an all-male scientific staff, I should be fired too. And that's not the way that's not the way, of course. And we're very conscious we don't. So think about at the one laboratory that he developed, we've had 12 Nobel Prize winners at our laboratory. There was Lawrence, and then there's Glenn Seaborg and Ed McMillan for all of these elements they discovered and isotopes. I'll talk some more about that. Emilio Segre and Owen Chamberlain for discovering the antiproton at the Bevatron at Berkeley. Donald Glaser and Louie Alvarez, he invented the bubble chamber, and Louie is the one who made it into this fantastic, productive scientific instrument. Melvin Calvin won his Nobel Prize for understanding the mechanism of photosynthesis. It's pretty important. Yuan Li for understanding chemical reactions, and then more recently, Stephen Chu for how cold atoms work and what you can do with them, ion traps and atom traps. And finally, and these are some colleagues that I've known very well, George Smoot and Saul Perlmutter, for basically understanding first the expanding universe and the age of the universe, and in Saul Perlmutter's case, for discovering that in fact it's not only expanding, it's accelerating. All these have been done, and all frankly in this theme of team science that Lawrence established. And just as one example of that, we talked about these accelerators. They realized that with these accelerators, they could actually build new elements, because you can take a nucleus, you bring in another nucleus, you glue it in for a short time. You have to do the chemistry to get those and see what they are. And so in the International Year of the Periodic Table last year, we got a plaque and all that about the fact that our laboratory is credited with discovering 16 elements on the periodic table, more than any other institution. Technetium, which has very important medical applications, ascertained. And then they sort of ran the table from 93 all the way to 106. We're all done at Berkeley. And so that's why some of these names are berkelium and californium and Lawrencium and Seaborgium. You know, the nice thing about this is you actually get to put your name on things in this thing. We don't do that in high energy physics. We didn't name the muon after the guy who invented it, but it is done for elements or the place. So remember that picture I showed you of the thing on the hill. So this is Berkeley Lab today. So that is the dome building. This is actually, I should have got a somewhat better picture of this, but this is our newest building. That's where our supercomputing center is. My office is here, and it stretches along the laboratory there. And just to say the scale of this, we have 3,200 people typically at the lab, about half of them scientists. As the scale of our research effort here is, basically it's bigger than any university in the country. That is just the scale of research effort. I mean, it's not well understood, but it's, bigger than, Stanford and the University of California, Berkeley, and the University of Chicago. We have a larger research effort there and still doing this world-class research at the level of national medals of science. So that's his legacy. Then you say, well, why do you do that? Why do you have national labs? And so this is the way I talk about this. It's mostly for great science first, but science in the nation's interest. Scientific solutions addressing national priorities like energy security, resilience, economy, the environment. These are things we get the National Medal of Science for. This is Paul Alvasados was my predecessor who did it for the quantum dots that are in a lot of your televisions today, developed there. Discovery science, that's the thing you get Nobel Prizes for. That's what Salt Perlmutter did. But unique scientific capabilities and facilities. In that thing where Lawrence had his biggest accelerator, we now have the Advanced Light Source, which is one of these sources for X-ray science. And that's the group that runs that today. So we do manage large research teams in a way that universities can't do. Important technologies with long, risky R&D paths, and a diverse group of highly trained, creative, and committed scientists and engineers. We get these brilliant young people and get them working on things of national interest, not just making better advertisements. I mean, just to be clear, that's part of it. We capture them into things. That's why you have a national laboratory. It's something that, it's not based on our profit return in 3 years, even though many of these things will eventually make profit for companies that build on our technologies. And these large facilities are a big part of it. We have facilities like the Advanced Light Source with these bright X-ray beams that do that biology, sort of medical research I talked about, but also chemistry and materials. Molecular Foundry, it does nanoscale science that actually builds new materials that have important properties we need for society. A high performance computing center. We have that has some of the fastest computers in the world working for the benefit of science. A network that connects all these things together in ways that are much more powerful than the internet in some sense, but it's run under a different protocol. And Joint Genome Institute, which came out of the Human Genome Project, but now does genome science, especially for plants, fungi, and the environment. So we still have ties to Lawrence. The last big accelerator his team did was an 88-inch cyclotron. It was actually designed and built by Lawrence's team. It actually, it has to do some tricks. It's not a simple magnet to take into account the fact that they're getting relativistic and keep it focused. They did that, finished in 1961. Lawrence died in 1958. He was only 57 years old. So he did all this, and from my point of view, as a when he should have just been hitting his stride in some sense. But we use this accelerator today. Jackie Gates here is doing, those transuranic elements that are the highest ones. She's measured the mass numbers for the first time of nihonium-113 and moscovium-115. I didn't know the names of these recently, but you can see this was discovered in Japan and this in Moscow, obviously. So this was sort of a fun thing we did at the lab. That building that had his accelerator, we have the advanced light source in, and we're now building was his 184 in cyclotron. We're building upgrading advanced light source. That's a big project that's going on. So we did a now and then series of things at the laboratory. So this was a fun one. I was standing up there, and they were trying to get a photo of me. I didn't know what they were going to do with it, and then they came up with this. So that was. But that is, this is a historic building, by the way. You know something about that here. So we couldn't do much to the outside. When they built this, they had to find a way of fitting accelerator into it because it's a very iconic building. This is the same architect who built this building who designed Coit Tower in San Francisco at that time. So I tell you, these advanced light sources, X-rays, what do you do with them other than medicine? Well, it turns out they're incredibly good at getting into materials and studying their structures in ways, even in real time, why things are changing. So these are some things were done where they were studying. This is the cathode for a lithium battery. A lithium battery, as the electrons flow around this and then charge and discharge, the cycle where in the cathode material, lithium ions go in to that structure and then they go out, go in, and over time they do damage. And in the end, that's why batteries fail and you can't charge them anymore. So this actually takes effectively movies of these lithium moving in and out. And so they can understand how they can change the structure in a way that they do less damage. That's the sort of thing. And probably every battery material has basically been through the advanced light source for getting analysis in this way. So, team science. This is what it looked like in 1945. This is what it looks like today. We're still doing these grand things. And I think the thing that best captures this, Louie Alvarez, the '68 Nobel Prize winner, said, Lawrence will always be remembered as the inventor of the cyclotron. But more importantly, he should be remembered as the inventor of the modern way of doing science. I think that's the primary message that I try to get across with the talk. You don't get a Nobel Prize for this, but it's had more impact than probably the second. So I just have to say what a fun job it is doing what I'm doing. So I'm just going to sweep through these, but just in 1 year, the breadth of science, our laboratory, there's laser plasma acceleration. These are accelerators that in this much space, they accelerate particles to the same energy as hundreds of meters of conventional accelerators. So we set a record for that. We do these sensor networks for air quality in Oakland that actually are so cheap that we can distribute them around the city and bring big data to understanding where the patterns of where the pollution comes from. Photocathodes that convert carbon dioxide into fuels. This is something that's going to be very important. They have these ways that they can use artificial intelligence to actually sift through which materials would be good for that. Understanding photosynthesis, Melvin Calvin first understood it, but we actually are now taking effectively movies of the structures of how photosynthesis works step by step. We have some of the most advanced climate simulations in the world today, which are getting more and more precise, and which is important. Well, simulations and including of extreme events so that they can actually predict them better longer in advance, so they can predict what time for people to get out. And finally, I'll just take this one, some open loop recyclable plastics. This is where they can take a white powder, make a plastic out of it, use the plastic, dissolve the plastic, and get back to the white powder. And if you think about what that would mean today, given the fact how many plastics are in the oceans, it'll take away. That's not in production yet, but that's the sort of thing we should be working. So the last thing Rich said, I talked about Bob Wilson, who was his graduate student. So Robert Wilson created Fermilab. This was him at the groundbreaking ceremonies for Fermilab in 1969, I believe. He's interesting too. He grew up in Frontier, Wyoming. I don't know what it is about these frontiers, these mountain states to produce these people at that time, early in the 20th century. But he was one of Lawrence's star graduate students. He established Fermilab as a place to build a high energy accelerator at that time, and I had the benefit of running that laboratory. This is the Cyclotron, this is the main injector, and this is the complex, of course, that's being used for neutrinos these days. He also brought a bit of the Mountain West along with him. If you ever get to Fermilab, you'll see the most popular thing there, of course, the bison and baby bison season. I lived on the site with my then 1 through 4-year-old daughter at that time. I must say, one of the best things to do to keep her entertained was to go and watch the baby bisons in season. That was hard to beat. And of course, those neutrinos are, in fact, the source of the neutrinos that we'll be doing the Dune project here. It will be the world's neutrino experiment. So last thing to say, I talked about this. I was working on the LZ experiment as a level 2 manager in charge of one of the systems up until March 2016 when I got this job, and I had to give that back to my colleagues at Santa Barbara. But what a treat it has been working at the laboratory here. What a treat it has been for me to work. And the important thing about this, it's not only the science that's exciting, but how rewarding it is working with these big teams. And it's just a very rewarding part of science, and it's something that we need to get people, young people, to do science. They have to understand how rewarding fun that is. That is, LZ is a great example of team science today. So, thank you.
All right. Thanks, Mike. Time for some questions.
Great. So how was Lawrencium discovered, and then how did they choose a name for
I'm sorry, how was?
Lawrencium?
Oh, I have to go back into the thing, but generally on that particular one, but generally what they would do at that time is they'd have these large nuclei that they inject small, that are near uranium, and they would they'd accelerate small nuclei that they knew had a good chance of sticking, inject, and put in enough protons and neutrons to make these heavier things. And then they needed to do look for the decays of the things that would show what they have. And so that was the general, and do the chemistry to separate the things they were producing. So that was the pattern with all those. And they sort of got they had the combination of the accelerators to do that, and the nuclear physics to understand what should go into what, and the chemistry to actually being able to do chemistry to separate these things and measure them. So that they sort of had a factory there of producing these things at the time. And then and of course they, at some point, they named then the Lawrencium Berkeley Californium, in honor of the fact that all that work went on in that environment. I showed you that 88-inch Synchrotron. We're thinking about there's an international campaign to look for the next one beyond where we are today. We're thinking about a campaign to do the one after that. We may get back into the business of trying to find new elements. It'd take a national campaign to do it, but we're seeing if we can get that going. That'd be fun.
I had heard that we are at the limit of the elements that we can have. Why is that?
Well, they're actually, it's very interesting. First of all, the only ones, uranium's the last one that is naturally available that you get by just digging into the earth. And that's because basically all the ones beyond it are unstable and decay. And so if they got made, they didn't last very long. And so the way we have to study them, and now why is that? How a to go back to this question, how nucleus is held together, you have all this positive protons are in one place, and they want to, electromagnetically, they want to repel each other and go flying out. So that's overcome by having the strong nuclear force that glues them together. Well, these two forces are fighting each other along with some other, and finally you just get, if you work through it, you finally get to the point where it's no longer stable. Interestingly, though, there are people who think there may be an island of stability a little further if we get, so if you can make things that are quite a bit beyond where we are now, you might be able to get stable nuclei. But it's this trade-off of the dynamics of the nuclear force, which holds the nucleus together, and the electric force, which wants to blow it apart. And it's the balance of those that leads to whether things are stable or not. And basically, if they're not stable, they just, you make them, they go away so fast you can't even see them.
Okay, other questions? Good, someone that's easy to get to.
I was at the 88 for many years, but back at the 40th anniversary, I was looking into a little bit of the history of the cyclotron and stuff. And what really amazed me was that in the early days of his work at Berkeley, that was before the Panama Canal was built.
Yeah.
So California was so isolated from the rest of the country that it's really amazing that science developed, to me, that science developed out there as strongly as it did.
Yeah. It's interesting also that the science that developed there developed in a somewhat different way, and it's because that maybe that isolation from the East Coast helped, and in two ways, and this big team science was a part of it. And what Lawrence was doing there, the other example of it was actually going down in Caltech with building the big telescopes. Those were actually the first two big examples of doing big team science projects, and they were both in California. He also had a color television company. Well, he sort of had the Betatron of color televisions. He had one that was very advanced, but actually didn't survive. I mean, not Beta, the Betamax thing. Betamax, yeah. Yeah. They've had that idea for the Casper Accelerator, and so you can tell me how that's developed, because I've lost. I don't know.
It is operational.
Yeah.
Has been. They're heavily involved with it, along with Notre Dame. And stars. Some of the processes with stars that lead to the generation of a lot of elements on the periodic table.
But doing it in a deep site where it's actually protected from radiation, from natural radiation, in the same way that's the reason we do all our experiments there. Yeah.
Oh, yes. Yeah, it's one MeV.
But that's the thing about there's different science you do with accelerators that are this big and this big and this big, and and they're whole different fields of science that you're addressing. With the biggest ones you're doing physics, some of the smaller ones you're doing chemistry, biology, and so forth. Yeah. And medicine, of course, which is the widest use of accelerators in the world, is actually for medical diagnosis and therapy.
Okay, so I think Mike will be. Oh, one more question.
Lawrence and Oppenheimer were both working at the same time, and I think Oppenheimer went on to do the atomic level. Could you talk a little bit about the relationship between those two?
Well, they work together. There were a lot of large egos in that group. Let me say. So in some sense, it was good they all found their own laboratory. Because I think the one characteristic they had, and I think I could say that about Lawrence and Oppenheimer and Wilson, is their ambitions were one where each one was going to need his own laboratory. I mean, it was good team science for a while, but you know, you have to know where it's time to start your own thing. That's what so that's what I understand.
Yeah.
But lab directors aren't like that anymore, however.
So Mike, we have a little parting gift
Oh, great.
for you tonight.
Oh,
Picture of Surf to hang
Oh,
in
yes.
your office.
oh,
Sure.
yeah.
So we'll ship this to you. You don't have to carry it on.
Yeah, well, that's great. You know how to be a good host. Well, it's great to be back here. To see it in a snow cover, this area is really great. I really appreciate it. I realize how much I'm just coming here. So, thank you. Thank you.
Thank you.